Good morning. This is E512 lecture number 14, and today is September 29, 2023. So we are talking about cascode. By the way, cascode, if any way you are keeping cascode, that is like as output impedance, then that will become voltage source or current source. Current source, right? Because that's the characteristic of any current source, that output impedance is very high, right? So as you are achieving very high impedance, means that is what actually happening. So can you tell me, find the cascode impedance over here? R out is equal to how much? Pragya. Hmm? What about M1? Okay. GM3, RO3, GM2, RO2. Okay, excellent, right? So do not forget these things. These things has to be on your fingertip. If you are in VLSI field, either you are in digital, analog, it doesn't matter. These are the impedances. Definitely you will see. Without seeing that, you can't run any show, right? So that's the problem. So do not forget all these things. It has to be on your fingertip always. Okay. Let's try these questions. Okay, and let's call this one as a surprise quiz only. Okay. Please submit these surprise quizzes to me today, whatever they are solving, and give them all surprise quizzes back. Okay. Whatever Puneet has actually said. These are impedance wise, output impedance has to be infinite. In terms of voltage, it has to be 0, right? So this is already known to us, and we have to design a current source which is PVT independent, right? So let's go that way. So generally we keep everything in ratio. That's the actually main highlight. We already talked about it, but again, like, it has to be in ratio, right? Ratio of resistors, symmetry in capacitors, and the matching of transistors. Everything is actually ratio. It's all about the unit value of the device has to be same, and it has to be changed by multiplier or by finger. Generally, we are going to use multiplier, right? So you can use your required multiplier with the unit value of device. So this is already we talked about it. Okay. Now let's learn one more thing which is important over here. If there are two transistors stacked on top of each other where gates are tied to each other, and it is like this is going to see W by 2 times L. Look at this. When it's like this, it's going to look at 2 times L. This current is flowing from both the devices are same, by the way. I is same, right? So that's going to give me I by 2L. Whereas if it is like this, if two transistors are in parallel, if both are W by L, this is going to give me 2 W by L, considering the current is getting divided, by the way. If this is I. As the geometry wise both are same, so the current is exactly half. There is no mismatch, nothing, because for device fabrication wise also, it's easy to have same copy, carbon copy is easy, W by L wise. So in that case, this is going to be 2W by L. Now look at the layout, how layout will look like if two transistors are in series. Okay, so this is now the real layout I'm talking about, not like the one which I used to draw with my with stick diagram. Here in this case you can see red color is actually polysilicon, W is diffusion, these are the contacts, and different metal lines are there. So in a chip design, if you look at, it's actually the elevated view. This is how it looks like, right? So if you want to tap out tap maybe body also, then it has to be from here, not from here, right? So you need this contact with the highly doped device, particular device like N plus or P plus has to be doped. So this is what and require. If you look from top, if you look at from top, it look like this one. Gate is here. This is drain. This is source, and as you know, whole white color is actually body. So if I want to take something, this is body. But I need a contact. This is known as the contact. Here also I made a contact N plus, and I made this drain. I made this source, right? And here also I need a contact to take it out. By the way, this is of polysilicon. So this is actually metal. This is silicon dioxide, and this is P substrate, right? So this is polysilicon over here, right? So that gate is here. I'm talking about that. And on top of that, we are going to keep some metal, and metal will be routed, and it will be connected to some other place, right? Are you able to follow? So this is the layout looking from top. If two transistors are in series or stacked on top of each other. By the way, note that drain and source both are interchangeable. There is no problem, right? So this becomes source, this becomes drain. Right? So let's look at this layout. How does it look like? So, okay. I made a mistake. This is for parallel transistor. So both the sources are tied together. This is gate and this is drain. So look at this. This is source, drain, and both the polysilicon gates are visible, right? So gate are tied together. Source are tied together. Drain are tied together. Understand, when we have to make such kind of structure, these requires contacts to take something outside, right? Or to go to the next level of the the layer. So these are the contacts, and note that this green color metal 1 and metal 2 are on different layers. Do you understand layers? Narmit, what do you think? On different layer means you just imagine a building where, let's say, 10 floors are there, something like different floors are there. Connection between one floor to another floor, let's say it's connected by a by a ladder, and that's actually all these stairs are treated as contacts, which is connecting from one floor to another floor. Each floor may have possibility to make the connection, but if you are making the connection here or here, they do not have, they are not overlapping each other. However, if you are connecting, let's say this is, assume that this is metal 2. I'm calling it metal 2 because it's available. Let's assume that it's on second floor of the building. And same metal 2, if we are passing through here, same metal 2 line, then there is a connection, direct connection. It's short circuited. If you do not want that, then you need, let's say I'm adding metal 3, means on third floor, or maybe metal 4, metal 5, metal 6, and note that the highest metal is available at the output, means visible at the top, and that is the place where we are connecting all the pins, right? So not from here, and here generally substrate is there, p substrate at the bottommost. That is how this whole chip is actually being made. So when you want to make, crossing of the metals, make sure that do you want short circuit or not. Okay, sometimes you need short circuit also, it depends. But if you want metal 2 and metal 3 short circuit, let's say this place I want short circuit, what I'm going to do, I'm going to keep a contact wherever I need short circuit between two different layers of metal. I'm going to use contact, right? So this is what we have done over here. Now look at this very carefully. All black colors are actually contacts. I pick up the contact from drain. I pick up the contact from drain. I I have connected through metal line, which is metal 2. This is vertically drawn, and horizontally I connected with metal 1, and same I did it with source, same I did it with gate. Are you able to see that? We are doing this with one of the simplest concept called HVHV. This is very popular in digital side, horizontal and vertical. So both the metals will be of different metal layer. If horizontal I chose as, let's say, metal 2, sorry, metal 1, and vertical as metal 2, that is what I did here. This will make sure that there is no short circuit ever will happen, right? So this is very important. One point to another point is actually, we are calling it routing, right? These are the contacts which we already learned. Metal layers, that also we learned, right? I believe, any doubt in this? Right? So generally people are using HVHV kind of layout making technique, right, where horizontal metal is different, vertical metal is different, right? So that you can do, there is no problem. And do not run any metal on any device. Means some people, to reduce the area, they are running the metal on this also. Let's say I am running, let's say metal 8 is going from here. Who is going to stop me there? Nobody is going to stop you, but some problem may occur later on, right? Don't do that. Okay, so don't do such kind of thing. Do not keep anything going on top of any device. So that is what very important. Okay, so this was for parallel, and if it is for series, let's say I made it wrong thing. If it is in series like this, so gate to gate are shorted. So look at this red color. Gate to gate are shorted by contacts and some metal lines, right? So gate outside is actually metal line directly. If you want to take it outside the chip to the pin, then you have to make more contacts. You have to go to the top floor of the chip. It might be 7th floor, 8th floor, or maybe 3rd floor, 4th floor, depending on the device. Like XFAB 180 has only metal, 4 layers are there. So 1, 2, 3, 4, and 4 is done, right? So 4 is taking you outside. Some place in 130 nanometer, it's UMC technology. It takes 8 layers. So accordingly, you can take, and last layer is metal 8. You take it outside. So this is on pads, IO pad. Direct. So this is one thing. So gates are shorted. Drain. This is drain. This is source. This is actually, I'm not going to call it source because I need to make drain to source connection. By the way, this is known as drain to source abutment in digital circuits. Maybe you will study that when you are going to study NAND gate or any other gates, right? So drain to source are shorted over here, and it's floating. However, I connected them horizontally by metal 1 and vertically by metal 2. It's in magenta, right? So this side source, this side drain. This is how you can make, you can make the layout of 2 transistors kept in parallel or in series. And always remember this. This is very popular question also, that 2 transistors in parallel is going to make 2W, and 2 transistors in stacked on top of each other, it's make double of length. This is very popular question. Most of the interview people are asking this question also. Right? It's simple, but still people can make mistakes in this. Right?
Sir,
Yeah.
which metal is used for finger fabrication generally?
Yeah, every metal. You can't get rid of it.
High conductivity, obviously.
You are asking about metal name.
Metal name.
It depends. Gold also, platinum also. Right? Okay.
Sir, the contacts are made of metals.
Yes, it's made up of metals. But some passivation and many other things are required. Right? Between 2 layers, it has to be something is there. Generally, metals might be same also. It might be same. Copper, aluminum, aluminum. It depending on technology. This is the current mirror which we were studying. So current mirror has only 2 main specifications, or current source or current sink. By the way, you can name it as source or sink also. Right? You need a current which is acting as a source or acting as a sink. So if it is coming like this from top and you want to use it somewhere on this transistor, let's say, then this is actually acting as a current source, right? Other place, if it is like this, when sinking, so it's current sink, right? So depending on the position where you want, you can design it. You can name it as current source and current sink. But most of the time, we are going to mirror it, or we are going to make the copy through multiplier, which we already studied, right? So multiplier, do not change multiplier. Do not try to do any fancy thing which is going to affect overall performance. So we studied this particular current mirror. By the way, this is current sink. So if I pump current of, let's say, 10 micro, and if this W by L or some value is given, so then how to make it 40 microampere? 4W by L. So 4 is actually the multiplier, and make the same thing. But if you remember, there is a channel and modulation also. So if you want to get rid of it, right, you can do this one. Does not make much difference, but with 3L, around 3L should give you the stable RO. If you are increasing more than that, might not give you so much benefit, right? So this is what we learn. Other than that, to evaluate whether it's a good current source or good current sink, we need to check two specifications: what is Z out and what is V min. What is Z out? Looking from the output transistor, if this is M2 and if this is M1, what is the output? RO1, right? So no problem. What about V minimum? Is V minimum is nothing but VDS, whatever is that. This one was VGS, right? This is what we learned, or we can call it V on also to make this particular transistor in on mode, right? So here, instead of writing it VDS, I can also write down V on plus VTH. So some different, I'm following the notation of right now Alan Holberg, because this is the book I am following, and it is exactly same as this one. And this is the value which is actually VDS set or V overdrive voltage, right? VOV. Right? So these are different books are following different notation. Left side is Alan Holberg, right side is Behzad Razavi. Okay, so right, so you can see it this way, that output is V on plus VTH, means this side is VTH is gone, one VTH is gone. Right? This will be useful further when we are going to do the complex calculation. This is just for your information. One transistor whose output is V on plus VTH, which is nothing but a VDS set, or this is equal to VGS plus VTH. The gate voltage becomes VGS. Just look at this way. One VTH is getting dropped. This is the only thing. Let's assume that I'm just asking. There is a, any chance here I got VGS plus 3 VTH. What should be the value of gate to source potential so that this transistor becomes in saturation? How much voltage is required here? Very simple. VGS plus 2 VTH. Okay, this is just to practice. For complex circuits, we will do that. Okay. So that's fine, right? We already talked about it. Okay. Oh, I'm making mistake, right? Minus. Yeah, that's a mistake. Right? VGS minus VTH has to be equal to. I made a mistake. My definition is maybe wrong. Let's write it down this way. VDS set. So then VGS is become VDS set plus VTH. So if this becomes VDS set plus VTH, then this becomes VDS. That was the right. This fine, right? This is also any way you can do it. I made a mistake. So if this is VDS plus VTH, then this is VDS. If this is VDS plus 2 VTH, then there has to be 3 VTH, right? So this is what we have to understand, and we have to follow that anyway. As I told, like this is also like used notation V on. V on is equal to VDS set. Okay. Now our next goal is we want to make a current source or current sink through the mirroring technique or the current mirror. Only two things are there. Output impedance has to be infinity and V minimum has to be 0. So how to make output impedance as infinity? Do you have any technique through which we can do that? We can do the cascode, right? If you are doing the cascoding, right, cascode of load, it will increase the output impedance. So let's go that way. If we cascode the transistor, where you can see now two transistors stacked on top of each other. I'm not drawing, which is source and drain, but of course lower potential will go to the source, right? Instead of having one particular transistor, we are going to have two transistors. So can you tell me, in this case, if this is M1, M2, and if this is M3 and M4, what is R out?
R not 4 into JLT into R not.
Right? So very simple. Now tell me, what is the value over here, which is actually making V minimum, right? Look at these voltages. I kept all the voltages. What is the gate potential? What is the gate potential? So here, if it is only this transistor, if you remember last time, we kept it here VDS. VDS is nothing but VGS minus VTH. So we kept VGS over here, plus and minus, and VTH is minus, so reverse polarity. Same thing I followed over here. I kept it over here. So in that case, what is the potential looking from here to here? So how much is voltage over here? Hmm? Is it correct or no? Right? Let's go back to the basics. What we were finding out here, VDS plus VTH. So that's why it was VDS, right? So one VTH is getting dropped over here. One VTH is getting dropped. So what's the answer? Hmm? Yeah. You're saying, sorry. What you are saying?
2 VGS minus 2 VGS.
2 VGS minus
2 VGS.
Right? This is one way to look at that. So there are many ways to look at the voltage. If you look at book, it is from here to here, it was VDS plus VTH, right? If you remember, from here to here also VDS plus VTH. So this will make 2 VDS plus 2 VTH, and output will drop with 1 VTH, so it will make 2 VDS plus VTH. By the way, we are trying to write it down in VDS. Why we are writing it down in VDS? We could have done it in VGS also, right? But I like this particular approach. Why we like this approach? Any guess, Abhishek? What do you think?
VGS, this is the output side.
No,
Because it will tell if it is in saturation.
no, that will give us power. Us means designer. If you remember, there were 3 equations of ID. One was going in proportional to GM, one was in this, that, right? And I told you, I follow one technique where I'm keeping VGS minus VTH constant. And that value, I fixed it to 250 millivolt. If you remember, more than 250 millivolt of VDS set will make sure that your transistor is in saturation. So if across this one and across this one, both individually, more than 250 millivolt individually, then both are in saturation. That's why I like everything in VDS, because each VDS is equal to, let's say, 250 millivolt, right? So I can find out the whole value very easily, how much value will be coming over here. So even though these are the variables, but still I know that numbers, right? That's why we are doing this. So in terms of VDS plus VTH, we can write down this way. VTH is known from the model parameters, right? It's a DC model parameter whose value might be depending on the technology. Let's say 300 millivolt or any technology, and VDS said I make it for 500 millivolt, right? 2 VDS, 500 milli. So from here to here, actually to make the transistor in saturation required 800 millivolt. Understand, these numbers are very important. If you know the VTH, now if you keep it here 250 millivolt, it won't work. The new number which came out of this equation says that across this individually 250 millivolt, but together in entire circuit it has to be 800 millivolt in total to make sure that this all the transistors are in saturation, right? So that's why this is required. So if I keep here 300 millivolt as VDS, then I have to keep here how much? 500 millivolt or 400 millivolt each, or whatever way you like. That's why I'm saying designer become powerful over here by keeping these values, right? So that is what required, and here that's the output voltage. So in cascade of double transistors, output impedance is how much? GM1, RO1, and maybe RO2, or you can say that if both the transistors exactly same, then it's GM times RO square, and V out is equal to, or V minimum is equal to 2 VDS plus VTH, right? So this is for the cascade current mirror. So, but if I want to make maybe more Z out higher and higher, I can do this also, right? Nobody can stop me this. Now I'm writing these values only, V1, VB1, VB2. You know how it's getting, created, right? So if this is M1, M2, M3, I can do this one, right? To achieve higher impedance. So what is Z out?
R naught 3 into GM2 into R naught 2 into GM1 into R naught.
And what about the voltage over here?
VDS.
Right? This is what we are seeing. And I know that 1 V1 is nothing but around 250 millivolt. So 750 plus, if it is 300, 600 millivolt, right? It's almost going 1.35 volt. Can you see the problem? Can you see the problem or no? In this technique, what is the supply in your technology? 1 volt. And by looking at this itself, you can say that look, in my technology, I can't go, stacking more transistors on top of each other. I can't do that, right? So you have to stop somewhere. That stopping is depending on you as a designer. You have to find out. Sometimes some people tune BTH also. Sometimes some people take this particular notation, meaning of this particular notation. So there are two kinds of MOSFETs. One, enhancement mode transistor, and another mode is depleted mode, right? enhancement mode is whatever we have studied till now, all were enhancement mode having this notation. Another one is obvious, this blue color with darker line, it's depleted mode. This is the one where VTH is equal to 0, where enhancement mode may not have 0. So that might be useful. Sometimes some people have taken patent also with keeping somewhere depleted mode, somewhere different mode, and they are taking advantage of both the transistors. That is also there. We'll see that maybe at some current mirrors where we are going to use such kind of techniques. Anyway, this is fine, right? So this might be useful in different technology, not suitable for 1 volt, right? So do not go more than that. But still, it's up to you. So that's all for today. Maybe we can talk further tomorrow.